Hello everyone, I am Pravin Agashe, and in this video I am going to cover how to find KZ factors for a movement resisting sway frame. And for this calculation of KZ, I have prepared one macro, and I am going to give you a presentation regarding the background of this macro, how and why this macro was developed, what was the necessity behind developing this macro, and in the last session we will see how this macro can be used. So let us go through a small presentation. Sorry. Why this macro? So the first topic is why this macro was developed, what was the necessity. Then we are going to see what are the components of this macro to understand the macro. What user has to What is the user's responsibility, what inputs are expected from user, and the last session will be how to use. So regarding the necessity of this macro, as we all know, while we are designing movement resisting frames, uh, we don't get the final section sizes at one go. So we carry out number of repetitions, number of repeated analysis. We go on changing the member sizes. We check the member sizes for the stress limits. We check the member sizes for the deflection criterias. So while doing such repetitions, unless we provide a correct KZ factors for each column, we cannot say our design is complete. So the user cannot repeatedly go on manually calculating the KZ factors and then define that KZ factors into parameters. So I have tried to automate this process, not 100% automation. As far as possible, what I have done, the user needs to provide the minimum amount of input, so that if you can reduce the user interface, automatically the human errors will be eliminated. So that was the main motto behind this particular development of this macro. So, secondly, not the time is also saved, and we engineers can avoid rigorous calculations, and also the results which we are going to get, that we are going to get in a user friendly format. In a present, we can present those results in our report, so that format will be very easy to understand. So this was the necessity of this macro. Let us go to our next topic. What are its components? So while preparing this particular macro, there are certain worksheets which I have developed. These worksheets include, first is the user guidelines. So this macro gives, in the first worksheet, this macro provides user guidelines. It also specifies what are the limitations and what are the prerequisites in order to use this macro. So it is not that it is not a blanket statement that this macro can be used for any of the structure or any of the Staad file. So in order to use this particular macro, we have to follow certain rules while preparing the Staad file, and if those rules are followed, then definitely we can use this macro. User has to note that this macro has been developed currently for Eurocode. So whatever the formula I have used in this particular macro, that I have taken from the Netherlands National Annex. So similar, this macro can be altered to suit whatever formula we want to use say if you want to use the formula given by AIC specifications, we can alter that particular code in this particular macro, and we can use the same macro, same Excel file. So secondly, let us go through all the limitations one by one and what are the guidelines. The first guideline is please use the latest version of the Staad Pro Connect. So this program, this macro will not be supported on older versions. The program is only valid for sway frames. And while defining the Staad file, while preparing the structure in Staad file, always keep in mind that to define a member or a beam element or a column element, the start of the beam should be on negative side, and the end should be on positive side of the axis, whether it is x-axis, y-axis, or z-axis. So that particular rule we have to follow in order to use this program. There is small limitation in this program that currently this program assumes that in a particular between two stories the column section is not changing, but it hardly is the what we say reality. When our height of the building is more than 12 or 13 meters, there will be a splice, and the section above the splice will be of lower. We can reduce the size at the top when we do not need it, and the splice is going to always fall between two floors. So that small limitation is there with this particular program. Portal frame under consideration should either fall in XY or in YZ plane. So the stat file should be prepared in such a way that the planes or the movement resisting planes should be either parallel to XY plane or YZ plane. Stat file should not be in a skew, should not be at an angle to the principal stat axis. So 99% we have that condition complied with. So at present, it is considered that beams and columns are subjected to sway and bending about their major or strong axis. So one more assumption, which is 99.99% true. Very rarely we came across a condition where we are going to provide a moment condition in a minor axis. So this particular program is aiming at, or he has assumed that the moment resisting axis is the major axis of the column. And the last limitation is this program is developed only for base units as metric. So as far as the base units are metric, this program will run fine. This program can also be developed for other base units also, but currently this program has been developed for only metric unit. Now let us see what are the user guidelines. User has to understand the limitations of this program. So right now the limitation of the program is it can only find the kz factors for 9 number of columns on a particular grid. So if there are 9 stories, this program will run fine, and in case we are analyzing a building more than 9 stories, then this program will not be able to find the kz factors. That is the limitation, but of course these limitations can be overcome by altering the code and altering the program. So since this is the first step of first attempt to prepare such a program, so right now I have kept all minimum possible criteria which normally are satisfied for 90% of the time. Since I am in working in oil and gas industry, hardly we came across very tall buildings. So all structures are technological structures, and these are well below 9 stories. The program is developed taking into consideration the Netherlands National Annex. That Netherlands National Annex we can see on the screen what Netherlands National Annex I have used, and the same formula will be used in this particular macro. All the yellow highlighted cells are the user inputs. So you can see in the program that I have, as possible, I have made an attempt so that minimum possible inputs are required from the user, and all other inputs will be taken directly from the Staad file. User has to define the rear beam end conditions. As we all know that the kz factor depends upon the joint stiffnesses at the top and bottom of the column. So also the stiffness of the particular beam will depend upon how the rear end of the beam is fixed to the column. So there are three conditions: fixed condition, rigid condition, and pin condition. Accordingly, the program gives us option to select the end conditions, and the user has to select. In the event the end of the beams are connected to column having their MZ released, simply delete the input in end conditions. Yes, so as whenever we are going to see the working of this program, we will look into this particular point. Another input user has to make sure he has given correctly in the Staad file is the LZ length, because program is going to take the LZ lengths of both beams and columns from the parameter list which we are going to define in our Staad file. So our parameters should be complete in all respects with LZ factors defined. Only KZ factors we are going to get from this macro, and those KZ factors we can readily paste into our Staad file. So this is regarding the limitations and user guidelines. Let us move on to next topic: components. The next component of the macro is the member list. As you can see on the screen, one member list tab is there in the worksheet. This member list tab user has nothing to do with this. This all this information is extracted from the macro by with the help of this macro into this Excel file, and this forms the basis of calculation for the KZ factor. So this is just for the information of the users, and user has nothing to do with this particular tab. Now here in this particular tab, the user is going to calculate the KZ factors for each column. So you can see what are the components of the this particular worksheet. At the topmost part at the center, you can see the warnings. So user has to see if there is any logical error he has made while giving the inputs to this program, or the error might be in the form of Staad file. If the Staad file has the errors, then also the same errors are going to reflect in this particular program. So the first necessary thing is our Staad file modeling and LZ factor should be correct. The vertical blue color line you can see that represents our column, and the red lines which are on the both sides of that blue line, these are representing beams. So you can see there is a yellow cell at the end of each beam where we can define the beam rear end conditions. Also, the property of the beam is automatically extracted from the Staad file, so user need not worry about that particular thing. Even the beam numbers are going to get extracted from the Staad file. On the left, extreme right and extreme left hand side of the worksheet, we can see how the stiffnesses of beams and columns are calculated. So these stiffnesses are used to calculate the top and bottom distribution factors or joint distribution factors uh, for each column, and using these distribution factors for top and bottom of the joint, the kz value for a particular column is calculated. So this was regarding the actual sheet where the kz factors are calculated. Let us move on to the next slide. We have already discussed a few of the user responsibilities. Let us quickly go through go through the same again. Uh, This particular first condition is known to everyone, that while using any OpenStat macro, we have to keep only one stat file open. We have to input the correct XY or YZ plane for the movement resisting frame. The correct design parameter number should be defined in this program. Appropriate LZ parameters, LZ factors should be given for beams and columns. And note that if user does not provide LZ factors for a particular beam or a column, by default Staad is going to consider the actual cut length of that particular member, whether it is a beam or whether it is a column. Appropriate beam rear end conditions is the user's responsibility. Follow the user guidelines and attend the warnings as applicable. So if these guidelines and responsibilities are followed, definitely we are going to get correct output from the program. So this was regarding the user responsibility. And the last session is about how to use. So we will shortly see how this program uh, can be used to find kz factors using a particular movement resisting frame. Now we are illustrating the macro, how to use this macro. And for this, I have prepared one example Staad file where the Staad file has total 9 stories. So total number of columns are 9 as per our limits. And I have deliberately considered different story heights for this particular structure so that our program can be verified. Let us see the 3D view of this particular structure. Here we can see that the main movement resisting plane is XY plane, and all the columns have their movement connections with the beams in their major axis, right? And the YZ plane has the bracings. So our plane of interest for calculating the KZ factors is XY. So we will quickly run through all the guidelines once again, and we will check whether all the conditions are complied with. So this is a sway frame we have already seen. All the starts and ends are in a way that which has been mentioned over here. So let us see quickly. Check one of the beam in x direction. Yes, the start is lying on the negative side of the x-axis and the end is lying on the positive side of the x-axis. Similarly for beams along y-axis, so the start is on the negative side and the end is on the positive side. Start is the green highlighted part and end is the blue highlighted part. Check for columns. Yes, for columns also the green highlighted part, which is a start, is on the negative side of the y-axis and the end is on the positive side of the y-axis. So this condition is also met. Let us check whether the units are in metric. go to input editor file, and we can easily verify through input editor file that units are meter KNS, and we are using the latest Staad Pro Connect edition. So that also we are complying with the user guidelines. User has to enter the inputs in yellow highlighted cells. Yes, that we are going to see. We have maximum 9 columns in a particular grid. So that condition is also satisfied. And let us see whether the user has defined correct LZ parameters for all the beams and columns. So here, deliberately what I have done, I have defined the LZ factors only for the columns. You can see here, LZs are only defined for the columns. And as I said, in case LZ is not defined for any column or beam, the program automatically takes the actual cut length of the beam or column. So in this case, our beam is 7 meters long. Each beam is 7 meters long. So we will see whether the program correctly takes into account the 7 meters in the absence of the definition of that LZ factor. So we have done with all the user guidelines and limitations. Now let us come to the actual sheet where we are going to find the KZ. Now finding KZ, if I can zoom it for you, you can see here there are two steps which are required. Step one is going to be performed only once. We are not going to perform this step one over and over again for our particular Staad file. The only repetitive step we are going to use is step number 2. The step number 2 is the step where actually the KZ factor is calculated. So in order to have our calculations for all the columns, now in this particular Staad file, how many columns we have? We have 3, 3 and 3, total 9 vertical columns are there. So we will have our grids defined for each and every column in the plan. So that definition user has to provide in this particular tab. So these two particular cells which are yellow, D4 and D5, it is for user to identify the particular column or particular file. Okay, so these inputs are not going to be used anywhere in the program. The only input the program is going to use is this Staad plane. User can also write here the project name. Now let us perform our step 1. As we said, we have to have all the necessary output from the Staad file in our member list item. So in this case, this is our old input, so we need not delete this. This is just for illustration. I am deleting the old input, so we need not the program automatically erases all the earlier output, so we need not do that. Now let us go to our Staad file, and our interest is to find the KZ factors for this center column. Okay, so go to plan, use beam cursor. Sorry, I'm sorry. First we have to extract all the information. So these are the columns. So go to plan, select beam cursor and select all the movement resisting frames. Even though the column of our interest is the center column, we can select all the moment resisting frame at one go, because every now and then we are not going to run the step 1 for different columns when all the information from the Staad file is uh, goes into that member list. So only step 2 we have to repeat again and again for different columns. So here the user has to keep in mind that for the step 1 geometry cursor has to be selected and not the beam cursor. So I have selected the geometry cursor, right? And the same instruction is written over here. If you can zoom in and see what is the user instruction. So the programming asking to use the geometry cursor to select the frames. So we have used geometry cursor to select these frames and simply click on this step 1. Now, as I said, there is no need to clear the earlier output. The program itself clears the earlier output. So just click on yes. We have defined our LZ factors in the parameter 1. So the default also the program is giving 1. So we will not change this. We will keep 1 as it is. Just click on OK. And the program is showing that total members we have selected are 138. Click on OK. This is just for users information. Now the run is completed, and now if you go to member list, we can see here all the beams or columns whatever we have selected. So their properties, their material, their cut length, their beta angles, their LZ factors, and their major and minor axis inertias. Also the node and their coordinates. Every information, what are the basic units, what is the date, what is the path of the file, every information is extracted by the program. So the next step is to find the kz factor of one particular column. So as I discussed earlier, our column of our interest is the center column. So I will select the center of the center frame, click OK, see the front view of the frame. Now just zoom in and refer to step 2. So the step 2 is asking the user to select the nodes and then click on this particular macro. So go to start file, select node cursor and select all those joints on the frame or on the column of our interest which are moment resisting joints. So do not select any joint where the beam is pin connected to the column. So what we will do, we will select all the nodes up to here and the rest of the nodes are here. We will omit this particular node since this particular beam is not forming the moment resisting system. So once these nodes are selected, go to the program again and just simply click on step 2. So in step 2, the program is asking us to enter the plane. So the default plane is XY and the plane of our interest also is XY. So simply click on OK. Once you click on OK, the program is asking us that whether the earlier output can be erased. Yes. The total number of nodes selected are 10, correct? Done. So now you can see here the program has calculated the kz factors for each column segment. For the top one it is 1.47, 1.51, 1.6, 1.78, 1.95, 1.84, 1.65 and so on 1.56. Now let us see whether all the information from the Staad file has been correctly reflected in our program. So we can see the bottommost column number is 55 and to the left of this column the beam which is there at the first story is 73 and 74. So let us go to the Staad file, let us zoom in, switch on the beam numbers and switch on the node numbers as well. So if we zoom on to this, we can see here the first column is 55. The program has correctly reflected 55. What we are here, the program is going to give you a view, Staad view looking towards minus z. So our view here is also we are looking towards minus z. So while looking into the Staad file, uh, keep in mind that whatever the view is suggested by this program, we are looking at the particular frame in that direction only. Otherwise, we will see here the 73 number is reflecting over here if we see on the opposite side. So in order to avoid the confusion, the program is asking us to look at the particular frame in the direction looking at minus z axis. So we are also following that, and since we are following that, we are getting the correct output. On the left hand side we have beam number 73, 74, 75. On the second story it is 75 and 76. Let us see whether yes, correct. So here also we have 75 and 76, and so on. If we go on to the top till top, we can see the last column segment is 63, and to the left of it we have beam number 89 and beam number 90 on the right hand side. So let us go to the top and let us see whether we have beam numbers, column number as 63. Yes, column number is 63. Beam number onto the left is 89 and onto the right is 90. Now just switch on, switch off the beam numbers and switch on the properties. Let us see whether the properties the program has fetched into the Excel sheet are proper. So the beams are HM 390 by 300. So all the beams at all the levels, all the stories are HM 390 by 300. So let us go to our program and check whether the beams are correctly reflected. HM 390 by 300. Yes, these are the Chinese sections. HM 390 by 300, 390 by 300, all the way to the bottom 390 by 300. One more thing which is important the user has to pay attention is see what is the end condition or what is the support condition of this particular column. So here deliberately, in order to illustrate the working of this particular program, the moment resisting direction I have kept this fixity in the MZ direction. You can see here the pin direction is on in the YZ plane, and for our plane of our interest, XY plane, we have fixity at the bottom of this particular column. So let us see whether the program has correctly identified the end condition of the column and has taken the coefficient or distribution coefficient accordingly. So go back to the program and just check here. Yes, MZ is restrained. So whatever the end conditions we are defining in Staad, these are correctly reflecting in our program as well. So since the MZ is restrained, we are having here factor of 0.25, correct? In case this particular restraint is released, then definitely we are going to have different value of this distribution factor. Also, as I told you, I have not defined any LZ value or factor for the beams, but you can see here in the absence of LZ factor defined, all the beams. So for beam number 90, the length, cut length considered is the default length, that is 7 meters, and for the beam on left hand side 89 also we are having LZ factor defined as 7 meters. So the program is working well. Now let us illustrate here by changing the end condition at the base. So here we have MZ is restrained. So we will run this program again, but remember we need not run the program again and again. We just have to repeat the step number 2. Correct? So step number 2 is the one which we have to repeat. So just change the end condition to, let us say, pinned in both directions. Go to supports, So this particular support condition is spin in both directions. So apply this particular condition here, assign, okay. Now again we have to, I will switch off the section properties for clear view. Then again go to front view and select all the nodes. Press Ctrl and select all the nodes at the bottom. So now all the nodes are selected. Now go back to and run just step 2. No need to run the step 1 again, as already we have extracted all the input. Uh, Press the step 2. XY plane is going to remain XY only. Yes. Yes. The program is done. Now go to bottommost part and check whether yes. Now here earlier, if you can see, the factor was 0.25 since the support was fixed. Now the support was fixed and now the support is released, so the distribution factor is also changed, and since the distribution factor has changed, the value of k is also going to change. So here till now we have illustrated that the program is running well since the user has provided the correct inputs to the program. Now what we are going to see, we are going to see these warnings. So when these warnings are applicable and how it becomes relevant to read the warnings after every run. These warnings are aimed at catching the incorrect input given by the user. So in case any user provides any incorrect input, and the kz factor which are derived will also be incorrect. So just to make sure, just to inform the user that some erroneous input has been provided to the program, these warnings are there. So one by one, I will first let us see. Let us check the program to its extreme. So as I said you that maximum number of columns it can handle are only 9. So let us add, let us select all the nodes. Okay. So here one extra column is added because of this. So these are the total 11 columns, 10 columns. Let us click on step number 2. Total number of nodes selected are 11. Now you can refer here, the number of selected column nodes exceeds the program defined limit, the program shall terminate. Select the column nodes up to or less than 10 and run the program again. So this is the limitation of the program. So right now the program has been aimed at to analyze the columns, only 9 columns in a particular grid. So that condition we have tested, and the program is giving correct message to the user that he has selected more than certain amount of nodes. So secondly, we can see here we have here a rigid beam end condition. Sorry, now right now I have clicked over here. So I will go back to the previous output. Now here, while running the program, I was not aware that one of the end condition for this particular beam was missing. So in this case, let us see whether this particular error the program has catched or not. So you can go to the serial number 3 and you can see here the end condition is missing for one or more beams. Keep the cell blank only in case the beam is pin connected to the column, that is no moment connection, and ignore the warning. So in this particular case, this particular missing end condition at this particular location was the error from my side, that I did not define the end condition by somehow that yellow cell kept I kept that yellow cell blank, but in reality that cell should be here. We have to enter rigid. Why we have to enter here rigid? Just go to the user's guide, and here you can see the different end conditions as per the code. So what the code is saying, if the member is ending into a member, you have to enter it as a rigid. If it is a simply supported, then you have to enter it as a pin. And if it is a ending in a very rigid wall, then we have to consider it as a fixed. So in this particular case, the appropriate end condition was rigid, and actually I did not pay attention to that particular thing. Now I have revised it to rigid, and once I revise it to rigid, you can see here the serial number 3 end conditions for all beams are defined. So the warning is getting vanished. In case we again deliberately delete here, just check, the warning is again appearing. So what it is implying that either the beam on to the left is pin connected to the column, which is not the case. So here we have to provide the end conditions. So we have to provide end conditions as a rigid. Once you make a correction in any of the input in this particular sheet, remember to again click onto the step 2. Otherwise this particular kz factor which was calculated was the factor when I had missed the particular input in this particular field. So again run the program. Yes. Okay, so I have selected 11 beams, so I will again go back to the program and I will select only 10 number of nodes. So here I have deliberately omitted the beam where there is a pin connection, right? Go to the program and click on step 2. Okay, done. So once by somehow the kz factor is remaining as k 1.47 only, but this will not be the case every time, and that depends upon this particular condition. So that user can go to the literature and check this condition. So this one error tracking, we have seen that it is correctly identifying the program is correctly projecting the warning when one particular end condition user is missing, user is not providing. Okay. Now secondly, let us check when this particular serial number warning is applicable. So beta angles for the columns. If we are analyzing a plane, if our moment resisting plane is a xy plane, if our moment resisting plane is a xy plane, then the beta angles of our columns should be 0. Now let us see whether this is the case. Go to properties, go to beta angles. Now since the beta angles are not defined, our beta angles are all 0, right? Now let us deliberately provide incorrect input to the program. Now create beta angle and just enter 90 here. And what we will do, we will select this column under consideration and we will change all the beta angles to 90 degree. So now if you can see here, if you see the rendered view, in rendered view, when we are saying that this is our moment resisting plane and all the major axes are along the xy plane, here by somehow by user's mistake he has incorrectly defined the beta angles as 90. Now let us try to run this particular program and let us try to see whether the program is catching that particular error from user or not. So again, go to select nodes, select all the nodes except this particular pin joint, okay, and then go to step 2 only, because uh, all other what we say factors are same. Only the beta is changed. So since the beta is changed, we need this information of regarding beta to be reflected in our member list here. So in this particular case, it is mandatory for us to go back to our step number 1 and run the step number 1 again. So what we will do, it will not take time. Just select the geometry cursor. Remember to select the geometry cursor for step number 1. Select all the moment resisting frames and simply click on step number 1. Simply click on step number 1. Yes, now you can see whatever the beta angle we have changed for one particular column, these are going to reflect in our member list. See here, all the columns which we have given beta as 90, so these are correctly reflected in our member list. Now go back to the same column of our interest, select the beam, select the frame, select all the nodes again and run this step 2. Now, when we are running this step 2, we have entered the plane as xy only. Now you can see this serial number 4. The beta angle for one or more columns are not correct. Verify if correct Staad plane is entered. Why it is asking this? Since in this particular frame now, if we see the rendered view, the major direction of the column, the major axis of the column, major inertia of the column is about x. So what the program is anticipating that the user is going to enter yz plane, but since our plane is xy plane, we are entering xy plane, and this was the mistake from the user side to uh, provide the beta as 90 degree for this particular column. So this way, you can see, if it is not that the whole column will get its beta angle, user cannot make this particular big mistake that one of the column will have different orientation as compared to the other columns in the frame. By mistake, while giving the beta angles to any other column, inadvertently one of the column element may get selected and it may get revised to another beta angle, and no issues. Even if in that case, if the user pays attention to all the warnings, he will be readily catching all the errors, and we can make the necessary corrections in our Staad file. So we have also seen how this particular serial number 4 is taking care of the beta angles of the column. And then the fifth warning. So here, the fifth warning, let us deliberately make one mistake in our input. Unless we make mistake, I will not be able to show how this particular warning is relevant. So go to our Staad file. Let us first correct ourselves. Let us revert this beta angle to initial value. Put 0, beta is equal to 0, and then here we are again reverting back to our original problem. So now all the betas are fine. Now select the column, select the nodes onto the column which are under consideration. And while selecting, what we are going to do now, as I told earlier, we do not have to select the nodes which are where the beam is pin connected to the column. So now I will deliberately select this, and then don't go up to the top, since my aim is not to uh, show you right now the kz factors for all the columns. My aim is to only illustrate you what the warning wants to convey to the user. So I will deliberately omit this top node, otherwise the program will not run, since the number of nodes will become 11. Correct? So go back to the program, go to step 2 and again run this program. And then you can see here uh, what the warning number 5 is stating us. Column LZ mismatch. The LZ value defined in parameter does not match with the node to node dimension. So here, why I have introduced this particular warning. This particular warning, the aim is the same, that if user inadvertently selects this particular node which is pin connected, the program is going to show the warning and the user will come to know what error he has made. So what is happening with this particular issue is that since this is a pin connected member, if you go to design parameters, you can see that the LZ for this particular column is defined as 7, right? The LZ for this particular column is defined as 7. But in program, what the program is doing here, program is calculating the difference in the y coordinate of the top node and the y coordinate of the bottom node to make sure the user has correctly uh, inputted the LZ value. So here what is happening, since we are selecting this particular node, the program is considering this column and this column as two separate columns. So program is not considering this particular column as a one unit, and the program is calculating the subtracting the y coordinate of this particular node to the y coordinate of this particular node, and program is saying that the LZ value for this particular column segment is 3.5, whereas I have defined LZ as 7. Since I have defined LZ as 7 and the program calculated value is coming out to be 3.5, only a warning is reflected here. You can see here. What is the column number here? Let us see. 57 and 271. So if you go to 57 and 271, 57 and 271, the LZ for both the columns have been taken as 7, and this is correct. What LZ is reflecting over this in this particular field is correct. The only thing is column as per the node coordinates, as I said, the program is saying that the column height is only 3.5, and this has happened because of the secondary beam connected to the column. So that was the reason I told you that I have included in my guideline that we have to omit such nodes, because these are not of our interest, since these are not the moment resisting joints. So we have now illustrated that here the last serial number 5 is also working correctly. So program is identified the error correctly. Serial number 4 is also we have covered. End condition error also we have covered, and this particular warning is going to be automatically satisfied since LZ for all beams are defined. So even if user doesn't define the LZ for any particular beam or column, the program is going to take the default value as the member cut length. So this was regarding the working of the program, and in case after working out the kz factors for this particular column, user wants to find the kz factors for this particular column. So what the user needs to do is simply copy this particular sheet, create a copy. You can give a different grid number to identify the column, and once the column is identified, repeat step number 1 we need not repeat since all the data, necessary data, we have in our background. The only case where we have to run the step number 1 is the case where we are going to change the member property, change the beta angle, change the end conditions. So in such cases, we have to go back to the step number 1 so that the correct data is reflected into this member list. So now we will go to grid B1. So suppose this is our grid B1, and what we will do, we will select here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here there is no secondary beam. So we have selected all the nodes. Go to step number 2. Okay. So now you can see here to the left hand side you cannot see any beam. So we are looking at the minus, we are looking into the Staad file in the minus z direction here, and we see that there is no beam reflected on the left hand side of the column. So and the same is the case here. So since we do not have any beams onto the left hand side of the column, we have all our beams onto the right hand side 73, 75, 77, and at the top 89. So let us check whether the program is correctly reflecting 73, 75, and at the top 89. So at the top 89, so beams are correctly reflected into the program. And here it is your choice whether you want to keep this is blank since there is no beam, there is no LZ. If even if you leave this input as rigid, it is not going to make any difference, but it is better that for the correctness of the input you delete these unnecessary end conditions over here. Yes, and for other end of the beam, for other beams on the onto the right hand side, we have already entered rigid, 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 rigid. So everywhere it is a rigid condition. Once we are ready with all the kz factors for all the columns in a particular structure or particular frame, uh, the remaining question is how to transfer the kz factors into Staad file. So, and the second question is how to represent these results in our report. So for the first query, just go on to the right hand side of this particular sheet. There you will find one column Staad syntax. Click on the filter and deselect the terms double X and blanks. Click OK. Once you click OK, you can directly copy these Staad syntax and paste it into our appropriate design parameter number. So this way the Staad syntax can be transferred to our Staad file. Secondly, how to represent in our calculation file. So for that, certain arrangement is made uh, in this particular file. If you see the page back review, go to file section, go to print section. So the whole page is accommodated in one single A3 size portrait frame. You can see what are the settings for this particular page setup. So this way we can take the PDF of this particular file and attach in our report. So that completes the working how to work with this particular macro. In case you have any suggestions regarding this macro, you can write to the mail ID which is there in the on the first page of the presentation. Also, you can drop a mail to me. You can drop a comment in our comment sections. I can send across this particular macro through the email ID, or I can even share a particular link where you can download this macro. So when you are satisfied, do write those comments in our comment section. And also in case of any queries or suggestion improvements, if you find any more scope in where we can save the time, where we can save the effort of the user, so do write those ideas to me. So I will definitely try to take up those ideas and improve this particular macro to the next revision. So till then, we will meet in the next session with some new macro for the new task. And till then, goodbye from me. Thank you.